Hello students, welcome to grade 10 real numbers part 5. Today we will discuss the last result of this chapter, that is, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p upon q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to the power m into 5 raised to the power m, where m and n are non-negative integers. In simple words, we can say that if the denominator can be expressed as product of only 2 as prime factors, as product of only 5 as prime factors, or product of 2's and 5's as a prime factors, then its decimal expansion will be terminating. Example, if in the denominator I have 8, 8 can be expressed as 2 into 2 into 2. That means only as 2 as prime factors. 2 raised to the power 3 into 5 raised to the power 0 can be written easily for this. Similarly, 125. I can always write it as 5 raised to the power 3, and this can be expressed in the form 2 raised to the power 0 into 5 raised to the power 3. That is 2 raised to the power n into 5 raised to the power m. Similarly, I take one more example, that is 250. It can be expressed as 2 into 5 into 5 into 5, that is 2 raised to the power 1 into 5 raised to the power 3. So in all these cases, whenever they are in the denominator form, then the rational number can be expressed as a terminating decimal. We notice all the above are expressible in the form 2 raised to the power m into 5 raised to the power n. So we can summarize that whenever such numbers are in the denominator of a rational number, the decimal expansion will always be terminating. But there is one caution, that is, if the denominator contains any other factor besides 2 or 5, then rational number can be expressed as non-terminating repeating decimal and not as a terminating decimal. Let's see few examples to see this. Example number 1, 17 upon 25. Now 25 can be expressed as 5 square. That is 5 square into 2 raised to the power 0. So the decimal expansion is going to be terminating using the result that we have discussed. Second, 8 upon 14. 8 upon 7 into 2. This is not of the form 2 raised to the power m into 5 raised to the power n, because 7 comes here. Therefore, it will be expressed as non-terminating repeating decimal. Now, let us verify it. When you divide, you will cancel it. You will get 4 upon 7. You can divide 4 by 7. When you divide it, you will find that the digits 5, 7, 1, 4, 2, 8 will continuously repeat, right? So hence I can say that it can be expressed as non-terminating repeating decimal. Now let us take some miscellaneous examples on real numbers that have been taken from your board papers. First one, will the rational number 51 upon 1500 have a terminating decimal expansion or a non-terminating repeating decimal expansion? So here in this, first of all, we will see that this is in the standard form or not. Very important. So yes, I see that 3 is a common factor of the numerator and denominator. So I cancel it and I get 17 upon 500. And prime factors of 500, they can be 5 into 5 into 2 into 5 into 2. That is 2 raised to the power 2 into 5 raised to the power 3. Therefore, the decimal expansion would be terminating, because this is 2 raised to the power m into 5 raised to the power n form. Question number 2. If n is an odd integer, show that n square minus 1 is divisible by 8. Here, we will take odd numbers in the form 4q plus 1 or 4q plus 3. Then n square minus 1 will be equal to 4q plus 1 whole square minus 1. I apply a plus b whole square here. So I get 16q square plus 8q plus 1 minus 1. 8 can be taken out common from here, and this 1 and minus 1 will get cancelled, and I have here 8 times 2q square plus q. Clearly it is a multiple of 8. So I can say yes, it is divisible by 8. Case 2. N square minus 1 can be written as 4q plus 3 whole square minus 1. Now this is equal to 16q square plus 24q plus 9 minus 1, which is equal to 16q square plus 24q plus 8. And from these three, 8 can be taken out common, and I have 8 times 2q square plus 3q plus 1, which is clearly divisible by 8, hence the result. Question number 3. Using Euclid's division lemma, show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Let a be any positive integer. Then on dividing it by 3, the possible remainders would be 0, 1 and 1 or 2. By Euclid's division lemma, there would exist quotient q and remainder r such that I can express a as a is equal to 3q plus r, where r is a remainder and it lies between 0 and 3. Or remainder can be 0, 1 or 2. Case 1, when remainder is equal to 0, then a is equal to 3q. This implies a cube is equal to 27q cube, which is equal to 9 times 3q cube. And I can always express this as 9m, where m is 3q cube. Case 2, r is equal to 1. A is equal to 3q plus 1. This implies a cube will be equal to 3q plus 1 whole cube. So this will be equal to 27q cube plus 1 plus 27q square plus 9q. We have used the identity a plus b whole cube. A plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. So this can be rearranged and written like this: 27q cube plus 27q square plus 9q plus 1. That means 9 times 3q cube plus 3q square plus q plus 1. If I replace this by m, I can write this is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Case 3. When remainder is equal to 2, then a can be written as 3q plus 2. This implies a cube will be equal to 3q plus 2 whole cube, which is equal to a cube is equal to 27q cube plus 54q square plus 36q plus 8. I have used the identity a plus b whole cube is equal to a cube plus b cube plus 3a square b plus 3ab square. Here a is 3q and b is 2. This can be written as 9 times 3q cube plus 6q square plus 4q plus 8. And I can replace this by m. So that means it is of the form 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. Hence proved that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Question number 4. Simplify each of the following and show that the result is a composite number. 5 times 11 times 13 plus 13. Here I can see that 13 is common, so 13 can be taken out common. So I can write 13 into 5 into 11 plus 1. Now solve the bracket. So you get 13 into 5, 56. This is equal to 13 into 7 into 8. And I notice here that this is having more than 2 factors. So whenever I have any number which is having more than 2 factors, it is a composite number. Right? Question number 4, second part. 6 into 5 into 4 into 3 into 2 into 1 plus 5. This is equal to 5 times 6 into 4 into 3 into 2 into 1 plus 1. That is, I solve this bracket now, and this gives me this is equal to 5 into 145, which can further be written as 5 into 5 into 29. Again, I notice here that this has more than two factors, that is 1, 5 as well as 29. So clearly it is also a composite number. Question number 5. Two tanks contain 504 and 735 liters of milk respectively. Find the maximum capacity of a container which can measure the milk of either tank an exact number of times. The maximum capacity of a container which can measure the milk of either tank an exact number of times would be the HCF of 504 and 735 liters. So we will find the HCF of these by any method. I have used here factorization method. So factors of 504 are 2, 2, 2, 3 and 7. And similarly, when I factorize 735, I get the factors as 5, 3, 7 and 7. So I can write it like this. 504 is equal to 2 raised to the power 3 into 3 raised to the power 2 into 7. And 735 can be written as 3 times 5 times 7 square. Now what is HCF? HCF is the product of the common factors. So common factor here, one is 3 and the other one is 7. So its product is 21. Therefore the maximum capacity of the container must be 21 liters. Question number 6. On a morning walk, 3 persons step out together and their steps measure 30 centimeters, 36 centimeters and 40 centimeters respectively. What is the minimum distance each should walk so that each can cover the same distance in complete steps? For this case, the required distance will be calculated through LCM of 30 centimeters, 36 centimeters and 40 centimeters. So 30 can be written as 2 into 3 into 5. 36 can be written as 6 into 6. That can be further written as 2 raised to the power 2 into 3 raised to the power 2. Similarly, 40 can be written as 2 raised to the power 3 into 5. So now what is LCM? For LCM, we take the highest powers of all the factors that are involved here and multiply them. So that gives me 2 raised to the power 3 into 3 raised to the power 2 into 5. That is equal to 8 into 9 into 5, which is equal to 360. Hence the required distance is 360 centimeters. Question number 7. Show that any number of the form 6 raised to the power n, where n belongs to natural numbers, can never end with the digit 0. 6 raised to the power n can be written as 2 into 3 raised to the power n, which is equal to 2 raised to the power n into 3 raised to the power n. Since its prime factorization does not have 5 along with 2 as a factor, therefore it will never end in 0. Last question, that is, two positive integers a and b can be written as a is equal to x raised to the power 3 into y raised to the power 2 and b can be written as x into y raised to the power 3, where x and y are prime numbers. Find the HCF of AB and LCM of AB. Now it is given that a is equal to x cube y square and b is equal to xy cube. HCF is the product of common factors, so that will be equal to x into y square. LCM is product of the numbers obtained by taking the highest powers of every factor that occurs in their prime factorization. So here the factors are x and y only. And what is the highest power of x? 3. And what is the highest power of y? That is 3. So the product x cube y cube is the LCM. Hope you enjoyed the session. Thank you.